Okay, today is just going to be electromagnetism, so that's good. Let's go. So let's start with the electric field. That's the chapter here. So let's start with electric field, but we're going to start with, of course, Coulomb's law. So Coulomb's law. Let's say we have some coordinate system, right? This is our coordinate system, x and y. Then let's say that there's some charge, right? Some charge q here. Then I have a vector to that charge q. Let's call it r of capital Q, right? Then I have another charge here, small q, right? Then we have r of small q there. And then, of course, we have the difference vector between them, which is this guy. And we just call this capital R, right? Like that. Okay. So now what we want is the force on this guy right here. So what is the force on this charge right here? The force is just, it's just Q times Q divided by 4 pi epsilon 0. And you can write it two ways. You can either write r hat, right? R hat, and then, of course, divided by r squared. Or you can write this as Q times capital Q, then 4 pi epsilon 0, then r the vector, and then instead of r squared, you have then, of course, r cubed, like that. Because, of course, r, we can just write this in green. So r hat is, of course, just r vector and then divided by r normalized. Okay. Perfect. Yes. And then we can explain the meaning here. So what does this mean, actually, this equation here? This states that the force onto some particle here, Q, that is, or we can say it's a particle, we can say charge. We usually, why I say particle, because when we start here, similar to mechanics, we start thinking in things as point particles, right? So a point charge, right? Same idea. And then later we're going to look at the sphere and etc., right? But in the beginning we look at a point. So you have this point charge here, Q, and the force onto Q is determined by the permittivity of free space. The permittivity of free space, I think, is how charge moves through, or you could penetrate the vacuum, right? That is this constant here, right? And then we, of course, I guess it's on pi because it goes everywhere, right? I'm not quite certain about that. Of course, it's r squared because it goes in all directions, right? That's very clear. And then, of course, it's q times q then, right? Because both of them are charges, right? And you can see from here very clearly that if both of them are positive, this is, of course, going to repel them from each other, right? If one is positive, one is negative, which we expect, they're going to, of course, attract, right? Similar to Newton's gravitational law, right? So that's the idea behind this. And of course, r is the vector between them. So you could say the distance vector between them. Not distance. What do I usually say? Not the distance. What do I call that r? Oh, even in that Griffith's book, you write that weird notation. I don't remember what it is. What do you call it? Relation vector. Relative vector was that, I mean. The relative vector was what I told, right? Okay. Yeah. And this, of course, is very similar to Newton's law of gravitation. Of course, if I just, for example, let's say I just called, what I could do is I could, of course, take, let's say, if we took all of this, and we call that 1, so all of this, so 1 over all of this, I could just do it like this, so 1 over all of this is equal to K, then we would have K times Q times Q, then R hat, and divided by R squared. And you can see how similar that is to, let's say, force of gravity minus G m, of course, divided by R squared, and in the R hat direction like that. You can see it's very much essentially the same thing, but for masses instead. And you can think of point particles the same. The only thing is that, of course, masses always attract, right? So that's a big difference, right? Okay, so what we have here also is that charges, they are conserved, right? So for example, if I took a balloon, I rubbed it against my head, what would happen is that electrons would move to that balloon. So the balloon would be, of course, negatively charged. If I put it on a wall, let's say this is the place I put it on the wall, and that's of course just plus and minus, and let's say we have minus and plus. And when I put it on the wall, of course the electrons, the negatively charged particles, are going to move away, and we get this unbalanced field right where I put it, right? So I get just plus, plus, and then when I stick the balloon there, of course they're going to attract, because we know from this equation right here that it's going to be a force there, right? And since it's a force there, we can of course model the balloon. So if I put the balloon, let's say it was here, I of course would have a force of gravity, and then a force, electrostatic force, let's say force of coulombs, like just Fc, for example, right? So a lot of similarities here. Okay, so there's something else too. We also have that there's also something else when it comes to the differences, is that masses add up, but not charges, right? The more mass we bring into the system, they add up, right? But not charges, because most charges are neutral, right? I'm not, usually I'm not positive or negatively charged, right? If I do the balloon, I can get some, since electron moved, I can get some positively charged here, not that much, but some positively charged here, right? But usually you're not charged positive or negative. Usually you just have a net charge of 0, right? And that's the reason why, even though the electrostatic force is a lot bigger than the gravitational force, that is the reason why we usually observe gravitational forces, right? I don't see an electrostatic force now, but I can feel my feet pulling me to the ground, right? Okay. Yes, and for example, if you think about the hydrogen atom as well, it's of course, it has one proton, and that proton has the charge E. I think that E, it's 1.62 or 1.9, 1.62, I think, and 10 times to the minus 19 coulombs. So that's proton, and of course the electron is minus E. I don't know if it's 1.602 or 1.6092. That doesn't matter. I'm just going to do theoretical physics. I don't need to remember that. Okay, so that's good. All right, what more do we have? Yes. Okay, yeah. Okay, yes. And also there's one small detail. So it's why can't I just call this for K? Like I said, there's something to do with calculation that we are going to learn later. That's just one small detail. And the last detail also is that superposition principle. It's actually just that systems like this are linear. So of course, if I have one force and I have another, if I add them up, that just, the force that is total is just adding them. So if I have force 1, that force 1 was electrostatic, and then I add it with force 2, that's just adding them up. There's nothing special there. So we can just add them. That's a super. So the total force I'm after is just adding them up. Nothing more, right? That's just linear algebra. Okay. Yes, we have that. And the third chunk I wrote to myself was just do the example, right? Okay. I think the example was something like this. Let's see. I think the example was that we had some coordinate system. And I put, I like to do this in blue. I put the charge. The test charge is there. Then we have one charge here, Q1. And then we have another charge there, Q. And the position here of Q1 is, of course, A. And then, of course, A. So it's A over there and it's A over there. And the position here is, of course, it's still positive A, but now it's minus A, like that. Okay, that should be all right. So we have to use both of those forces. We pretty much realize that if you look at the vector, like this will point here, that force, and this force will point right here, they will cancel in the y direction. That's pretty clear. But we can just calculate it anyway. Okay, so the force 1, let's say force 1, let's call this guy Q1. This guy is Q2. I do blue, whatever it should be. So my mind gets annoying if I don't do that. So F1, right? So F1, and like we said, and we also can state that Q1 is the same as Q2 in terms of magnitude, right? So F1 is just Q times Q, like that. Then we still have 4 pi epsilon 0, right? And then I, of course, have that. Let's say, what do I want? Do I want the unit vector or the vector? Maybe R is better. Let's just write R. So the R vector and then R cubed, like that. Okay, and then we have Q and 4 pi epsilon 0. And of course, the R vector is pretty easy. It's just the opposite way. So I have to get to there, right? And if I want to get to there, I have to go minus A and minus A. So this is just minus A and minus A, like that, right? And R cubed, that's pretty nice. That's very neat. That's just 2A. And then we want, so we have 2A. Oh my days, more. Let's see. How can I do this the most simply? I want A and A. Okay, I can just write it. That's the best thing you do, just write it. So A squared plus A squared times 1/2, then times, of course, 3. That's what we have, right? Keep on going here. And then, of course, I have Q, like that. I have 4 pi epsilon 0. And then I have minus A and A. We can, of course, just take out minus A and keep the direction. That's, of course, neat. So I can just say minus A, like that. Then we can just keep minus 1 and minus 1. Yes. Then I have A squared, right? That's just 2A squared. That means that I have the square of 2, like that, but then I would have another 2 because I have cubed, and then I would have A squared and another there as well. So I think this will be just A squared and you will go out. I think that's pretty much correct. Yes, that should be correct. I have written it a bit weird, but who cares? But I think that should be very much correct. Okay. And of course, if you do F2, it should be the same, just the coordinates there are going to be different. So it should get the same. So I should add Q over Q, 4 pi epsilon 0. Instead of minus 1, in order to get back, I have to go up. That's positive. So I, of course, have 1. And then I have to go back in the x direction, and that's of course -1. But otherwise, this should be exactly the same, right? -a, and I took out... now I can't get rid of that a. Oh, my mistake. I took out -a. Then I shouldn't have minus there. My mistake, yeah. That's true. That should be just 1. Okay, and I can take out a there like I did, and I can have, just to make this a little bit more, 2 squared, then a squared, right? Okay. Then we can, of course, add these up, and as you see, the y component cancel out. We get 2, and 2 goes away. So f in total is, okay, just to be peculiar, I could just say f1 plus f2. That's, as you can see, 2 goes away, so I just get q over 4 pi epsilon 0. Then I have, of course, I should write it there. So I just have a squared times the square root of 2, and then in the x hat direction. That should be correct. I'm pretty certain of it. Okay, very good. Yeah, now we have finished the column force. Now we can go to the electric field. That is pretty simple. So, what if instead of this case that we had here with just, let's say above with just 1 charge, let's say that we had a lot of charges. Something like this. Oh, that was a stupid coordinate system. So here's our coordinate system, not so stupid this time. And let's say I had Q1, I had Q2, I had Q3, I had Q4, I had Q5, etc., etc., right? Okay, and then I placed my point charge somewhere, right? And we call this vector up here R, and this point in this R is actually the only one we care about. Why is that? Because we are going to move this guy around, right? But these are going to be static. That's the idea here. Okay, but I'm just going to draw those vector anyway. So this is Q. Could just say Ri. Just say Ri. Oh, you more on R5 we can go with, yeah. Then I have another vector there. That was a nice vector. R1. Then I have R4, etc. I'm not going to do the rest. So now, if I wanted to calculate the force on Q, you can use the superposition principle. I just add up all of those. So I Q of I, right? I still have 4 pi epsilon 0 like that. And then the relative vector, of course, is going to depend where my test charge is. So I need R of I as a vector, and then, of course, divided by R of I cubed, like that. Okay, pretty neat. And Q doesn't depend on all of this, so I can just move Q out. And then we have something cool here. I can just do this in blue to make it clear. We have Q of I divided by 4 pi epsilon 0 Ri, the vector, and of course R of I cubed. And we call all of this the electric field, where we depend only actually on R, and of course Q of I and R of I are given, like that. I think R of I, the vector, yeah, are given, right? Because we are thinking like in terms of, let's say, if I want to look at the gravitational field, right? This is the electric field. If I compare it to the gravitational field, if I look at a comet and I placed it somewhere in the gravitational field, that is what I'm trying to do now. And let's imagine that the planets are static. That is how we think about this. Okay, so that's the idea. That is why we only depend on R, right? Okay, And we write the definition like this. We say that the electric field R is equal to, of course, the force. That should be correct, yeah. So I should, let's see if I'm a moron or not. No, it's correct. The force, and then divided by Q. And then we are going to let Q, oh my god, we're going to let Q approach 0. Now, why do we want Q to approach 0? The idea for Q to approach 0 is like this. It is so that, right, when I'm if I wanted to measure the gravity on Earth, I can do that easily even though I'm standing on it. The reason why is that my contribution is not that big at all, right? Compared to the planet, it's nothing. It's pretty easy to measure. And we're thinking the same thing here. We want our charge, or test charge, to not affect the charges, right? So that is why we're letting it be as small as possible. Why are you blue? Okay. So that's the idea there. Okay. And we also call R, this R vector here, we call the observational vector, I think. So, observational point is actually what we call it. Yes, because like I stated earlier, we're going to place R, and we imagine that all of these Q1, capital Q1, Q2, etc. are static, and we are placing a test charge that doesn't affect the distribution here, right? We can just place it anywhere. That is why we only depend on the vector that leads to where I placed, of course, the test charge. Okay, and this, again, like I said, has a lot of similarities to gravitational field. Let's say I wanted to place me anywhere or a comet in the gravitational field and see how it responded. Then I can measure the strength of that field, how it behaves, etc. Right? Okay, so that's theory. And for the rest, we're just going to do the tasks. So the tasks here, how you turn on kjøkkediff, that's good. Let's see, that's not what I wanted. I wanted this guy, right? Yeah, that was what we did earlier. Yes, okay. And this was this guy, and I wanted that tornado stuff, right? Okay, yeah. Okay, let's just do some tasks. We do this on the fly. Okay, so you have seen the movie Twisters, and you start to discuss how the wind is inside a tornado. Now make what do you call this word again? Let's just say a quick drawing. So we're going to make a quick drawing of how a tornado will be. So of course I imagine it be something like the strength. I didn't know how, because I know if I threw a plate that of course the velocity is going to be bigger because the radius is going to be bigger and it's going to cover more length, so the velocity is bigger, but that's not true for the tornado. I guess because you have to pull particles around, so the velocity is actually a lot bigger at the center. The closer you are to the center, of course, at the center it's 0. That's one of the questions as well. But the further you are, smaller it actually is going to be. And of course it's going to die out. That makes sense, but I didn't know that it also got smaller, but that of course makes sense. So something in the ballpark of this, like we have bigger velocities closer, right, to the center, but the further we go, the less the vector field will of course weaken. Okay, compare. No, I'm not going to do that. How is it in the middle? Like I said, of course it's 0, and far away it's 0 as well. It's not an infinite tornado. Can you describe this field as a vector field? So my first idea for this is that, of course, we have Coulomb's law, so I can just use something in that ballpark. I just need it to twist in that direction. So in order for something to twist, right, I just need, if I said that we had we did minus y and then x, right? Because it means if I go x, no, not like that. If I look at some coordinate x, right? This is going to be the field. So let's say this is not the field I want, but this is just how I may imagine this. Okay, so if I took some coordinate x, right? So I walk this guy over here. It's going to move in the y, right? If I walked some y up there, it's going to move in the minus y, right? So minus here. That's the idea we want, that twisting effect. Okay, pretty neat, but the problem with this here is that it doesn't die. And I also want it to be the biggest when it starts, so we can just use whatever we had. If, for example, v x and y was equal to we could have something like something similar, some constant, right? I just call it k because from what we had, and then I could do the same thing. I can have minus y comma x like that. Then it could of course divide it by the distance, right? Because when it goes so radially, we want it to weaken. And of course I could just do the r squared. We are very used to r squared formula, so why not? That works. I think you can do some exponential as well, but that works. This was programming. Oh, let's try and do this from scratch. That will be more fun. Okay, I want to do this from scratch. Okay, because I think, yeah, can you visualize how this looks? So let's try and do this from scratch. That's good training. Okay, so let's call x is equal to, I want start, and I want stop be something like, what, 20? Yeah, minus 20, no, maybe 10, minus 10, 10, and then I could say n is equal to 20 plus 1, right? Because you get the step size get weird, so I can do that. Then I just do linspace, and then I can do start, stop like that, and of course I could do the same here and use y. That should be all right. Okay, let's now create that vector field. So def v and then x comma y, right? It takes some x and y. That's the idea. We of course need that mesh grid. So I can say rx comma ry is equal to np.meshGrid. Then we have x comma y, and this one is important indexing because it actually does it the other way. So we want that ij. We have rx, ry, and I want now is r norm, and I could just do np.square root like that. np.square root, yes, of rx squared plus ry squared, right? That should be it. Then for our function, we just say that velocity is equal to, what was the function? I had some k, right? So I could just say k equals to, I don't know, 2.3 something weird. I don't care. Maybe that's a lot. Maybe something small. That would make more sense. That's how usually these formulas are. 1e minus 5, something like that. Yes. And then velocity is just k. What do I want? I want it in the x direction. Yes. So I could just say vx. Yes, that would make more sense. So vx is equal to k. Then I can use the formula I've written down that we looked at. That now it's going to do the opposite. So I need x. The x is going to be, it's still the same. Of course, it's just minus ry. No. No, I don't want that. I want the direction. Do I want that? No. Can I just say r? Because it's r, yes. Maybe. I need that norm. Okay, just do the norm first. So k divided by r norm squared, and then we can multiply. I just need the r direction. Yeah, I'm a moron, of course. The x direction is going to be minus ry. That's it. Yeah. And then we can do the opposite. Yes, yes. Then I have rx. Yes, this works. Then I have vx, vy, like that. That should work. Now I could do plt dot quiver, and what would quiver need the data? And data is vx comma vy. Ooh, I need vx comma vy is equal to v and x and y. Yes, yes, plt plt.axis, isn't that equal? Yes, and then plt dot show. Yeah, that should work. So p test dot I. That was pretty bad. But how didn't that work? Now this goes. What did I have? R cubed maybe? Because I have the vectors there. I don't have the unit, so maybe I need but I have r. Maybe I need r cubed. Either that or oh, I'm a moron. No, it was not that. Okay. Let's see. Minus ry is correct, but now this field acts like this. I was close, at least. Maybe it's because my k is not fun. Maybe it's that? No. Yeah, it's bigger here, but my direction is completely off. It's the direction here. Of course it is. So what did I do with the direction here? The lint space is correct. Rx, Ry. The indexing, of course, this norm is correct. K is correct. V of x. Why isn't this correct? It's not. I'm not divided by this. I hope it should understand that. That shouldn't be any problem. Why is this problem? Let's see. No. What is up with my direction? Minus r of I. That is our idea. It should be correct, shouldn't it? What? I have in the x direction, I have minus r of y, right? What's wrong with that? Then in the y direction, I have positive x, right? God damn. Let's see what I did a mistake. I've done this seminar. I had k. What? I did this? That shouldn't be correct. I did this. This is what I did. Minus times minus ry. I did the mesh grid here then, but still, that should be correct. K is equal to 5. This is also good. Oh, the quiver is the wrong. Damn, I'm a moron. Of course I'm a moron. Rx, Ry. There you go. You have to start from some point, right? Of course, yeah. That was not. I should actually just do this, then do this. Just say Rx, Ry. Goodbye to you. And now it should work. Of course, you start at quiver is starting at some point, and then you're telling the vector to go. This is the direction for vectors. This is where we are starting. God damn, now it should work. No? This is programming. Let's see, what did I do? Maybe this one was too crazy. What was the thing I had here? 5. Okay, let's see. Rx, Ry. Rx, Ry minus Ry. Vx, Vy. Oh, that's of course not correct. My mistake now. Yes, okay. This one looks a bit weird, but it works, right? You can see we have full strength here at the beginning, and the further we go out, the more the tornado dies, of course. And of course, when it's 0, there's no tornado then. Yes. Okay, happy with that. The next task in the storm, but this is just what we did, so I don't get why when this goes to 0, is it defined here? No, there's no defined there. Can't define if this goes to 0. Okay, let's, oh, not 5, 4, let's do 4. 4 is, yeah, we can do 4, that works. Let's see, so we have a vector field f, and f is equal to, I hate writing it like that, so I just write it, y plus 2 in the x hat direction. Then we have plus just 2 in the y hat direction. Now the task is write up the integral for a line alongside the x-axis from 0 to 5, and we should parameterize this line with a variable t. Okay? To parameterize, we can do that pretty, because we're moving alongside x, it's pretty easy. It's just r of t, it's just t in the x hat direction, right? So that works very well. Okay, we have to, of course, in order to do line integral, we have to do dr dt, like that, and of course that's just x hat direction. That makes sense. That's what we want, and of course I have to do f, and then I have to do f of r, so I have to place r into f. When I do that, the only x value I have is t, but there aren't any x values here. So the answer is, of course, just 0 plus 2 in the x hat direction. And then, of course, there's no y coordinate. But that's just 2. Did I mess up something? Oh, that's just 2. That should just be 2. Or am I drunk? No, that should just be 2. 2y. Let's see. Sometimes your mind is like stupid. But that's all right. Okay. Yeah. No, I know that's correct. It's correct. And I've written that integral, and I should write it from 0 to 5. Okay. Not cute orange. 0 to 5. So let's see. The work, you could say, a line integral for f dot dl is of course the same as going from 0 to 5 for f of r, which was just 2 and 2, and then we multiply that by just x hat, so just 1 and 0, and it's dt, like that. That is just, of course, we get 2, so 2t and 5, and that's just 10. Perfect. Okay, if y is equal to 2, you just get y there, so it's just going to be 2 times 10, and that's going to be 20. Okay, let's go to the next. Your friend Q has solved the task by parameterized with the position x. She had done that, and she states that this can't be right, because a line should be parameterized with the variable t. Is this correct? Has Q does it? Yeah, it's correct. It doesn't matter. No one cares if you use phi or t or I don't know, whatever. It doesn't matter. It's just the statement, maybe the geometric interpretation is weird, but of course this is all right. Okay. As long as you're not what you say, as long as you're not violating any mathematical reason, is of course all right. Okay, find the line integral for a line y is equal to 2x from 0 to 1.2. We can of course parameterize this guy. So the line is y is equal to 2x. So we have r of t is equal to 2 times t in the x hat direction. I'm going to get back to the video. then plus, then we just have y hat, right? Okay, y is, and we still have our vector field, right? Okay, I need to just get that guy as well, right? Okay, like this, and then I have r there. Okay, same procedure. Then I just do, of course, dr, dt, 2t, that's just 2. Yeah, 2 in the x hat direction, right? Y isn't anything. And then f in terms of r. What is f in terms of r, right? There is 1 now, so y is... Do I have a... What? Am I drunk? There is 1. So y is 1 plus 2. Is that correct? That felt weird. So I have y 1 plus 2 in the x hat direction. Yeah. Plus 2 y hat. Okay. Let's roll with it. And what did we have? We have... It was from 0 to 0 to 1, 2. But we have just parameterized and just in x. So it's from 0 to 1, actually. Okay, so the t value is from 0 to 1. And we have f, that value there. So we have 3, and then we have 2. And then we multiply that by, of course, r of t, which is just 2t, and then 1. This seems weird. This seems, have I made some stupid mistake here? No, of course, it's the derivative, you moron. I knew it. So just 2. 2, and then, of course, 0, right? And dt. Ah, now it makes more sense. But did I forget something here? Y, f, that's just y of 2? This feels weird. Like I've missed something. I had y plus 2. So the x, just plug in the y value. That's just nothing at all. That's just 1. So I would have 3. And it's just still 2y. Yeah. Okay. Let's see if I'm a moron or not. 3 times 2, that's 6. There is something wrong here. I can't feel I have done something wrong. Why do I have 2 and 0? That was because dr dt. Yeah, that's 2 still. Yeah, what have I done here? I made some obvious mistake for some reason. Because I believe I should get 7. Now I get integrating 6. 2 times 0, that's just 0. And I get integrate from 0 to 1 here, I just get t. That's not correct. 3 times 2 is 6. That shouldn't be 0 on my r of t there. Is my parameterization correct? 2t? Y? Is there something I missed here? So let's see. Y was equal to 2x. That's 2t in the x hat direction. Right? Y isn't equal to... Or am I... Is it the y value? Maybe I'm drunk here now. Ooh, maybe it's the y value. Yeah, maybe I'm an idiot. If I move in the x direction, I just move in the x direction, but y increases by 2. That is it. I am a moron. 2t. That should be it. it should be 2y, but that should be t as well, shouldn't it? If I parameterize a line, I move my coordinate, I'm going 1, then I go 1x, and then of course 2. Yeah, that should be it. I think I was just a moron. Either I'm a complete moron, or this is... yeah, we'll see. That's just x hat, or I can just write this in terms, now it's easier. 1, then this should be 2. Shouldn't that then be correct? Let's see. If I have 1, and then 2, 3 times 1, that's 3 plus, yeah, that's correct. 3 times 1, that's 3, plus 2 times 2, that's 4. dt, all this is going to just be 7. That should be it. I think that's correct. What did I do? Of course, that was the parameterization. R of t, right. If I want to understand the line is just that when I walk 1x, so walk in the x direction, I should go up with 2. Yeah, that should be correct. I don't know why my brain was stupid. That's all right. Can you parameterize this line? Is there another way of doing that? Does this parameterization mean anything for line integral? Why not? No, it doesn't. Doesn't matter how you look at it. So as long as you're not violating any mathematics, it's all right. Like if I looked at the line, if I did this in polar coordinates, or if I did the Cartesian, it doesn't matter. If I still arrive at the same position, regardless, it does not matter. Okay, 5. Was this a good task? This one is good. Okay. Yeah, let's start with this one. Let's see. I should finish in at least, yeah, maybe 15 minutes more. Okay. Let's see. So a line along a curve. Yeah, that's what we did. Now I need this against the current. Okay, so you're supposed to fill a bucket from a river. Assume that the velocity field in the river is uniform. So it's just v0 in the x hat direction. Assume also that the velocity, or the current, I mean, of water isn't affecting the bucket. This is obviously not right, but just assume so. You wish now that to fill the bucket as fast as possible. How should you then hold it? Of course, I actually use this when I've explained I explained this integral. Of course, you should hold it with the same direction as the normal vector. Of course, if rain is pouring down, if you hold the surface, you're catching more than if you're, of course, not holding it perpendicular, or if you could say parallel to the normal vector, or the surface itself should be perpendicular to, of course, the direction of the rain, right? Nothing special. Surface integral flux is equal to this, where call this flux, find the flux for the bucket with the orientation you found in task A. So it streams into the bucket, so let's say it's positive. So which means that the flux, in our case, this looks like a Pokemon every time, is just the velocity field, and of course ds like that. But that's pretty neat because we just have that v0, so v0 can go out. And of course we have what is the surface, and both of these are going the same direction, so we have x hat and that normal, which means that we actually just have ds here, and integrating over s is just the surface, so that is just v0, and we 4 pi you moron 4 pi v0, and of course pi r squared, right? That's just the answer. Okay, so just the area of the surface. That should be it. Yeah, then they just did vs, but it's the same idea. Oh, not that. What happened if you instead hold the bucket with the current? So with the x-axis, of course, if you're not feeling anything, so there's no flux, so it should be 0. That's the answer. Your friend Q looks you turn the bucket around, say that it doesn't matter which way you're holding the bucket. The flux is only depending on the cut, like where that bucket goes for the bucket, and the size on the opening for the bucket doesn't change if we turn it around. So the flux should be the same. No, what is wrong with this argument? Physically, that doesn't make sense. If I turn it around, of course, it's going to bump on that back, right? And also, there's direction as well. We have negative and positive flux as well. So which way is positive for the surface S? What does that mean for the flux? Does it mean to describe the surface with a vector S? Yes. Physically, what does this mean if you change the sign? Yeah, that's like turning the bucket around. So it's all right. What if the surface S wasn't a surface? What is not a surface, but what if the surface wasn't a plane, but actually what do you call it? Hemisphere? Yeah, a hemisphere. What will be the flux then through the surface with the orientation you choose in A? Is this the same? So you can actually calculate it, and if you calculate it, you get the same answer. It's more complicated. I'm not quite certain why you get the same answer physically, but we can calculate it. So if you have this surface here, right? It's somewhat hard to make this drawing, but we're doing our best. Okay, that was not my best. Like that, and then I could have like, so it's a 3D surface like that, right? So like that. And this is of course the bottom of the surface here. Maybe I put that in red. Like that. That's not that bad. Okay. So this here is of course, this is the height here, right? And that's of course just going to be R. We have Z, and I have X and Y. I mean, just now turn the coordinate system around instead of in the X direction, just in the Z. That just makes it a lot more simple, right? Okay, so what we need to do now is, of course, writing this. I need, of course, it was that vector over S and then ds, right? Now the vector, let's see, we should do this in parts. So the vector now is v0 z hat instead, right? And ds is actually pretty simple to model. If you use spherical coordinates, you can see it pretty easily. So if I took some chunk here, that chunk is pretty simple. It will always go in the radial direction, so I can use this as a vector. It will be r squared. I can just write it because first we need to go in this direction, right? This direction is pretty simple. That's just d phi. So I need r d phi, right? And then I need to go in one of these, either up or down, but it's like up here. So I need to get there, then I need to use the angle as well, and that's just r and sine theta to get there, and then I need to do d theta. And then lastly, we need a direction, which is of course just r hat. This gives us r squared d phi d theta. Oh, I should just use that at the end. That doesn't make sense. Sine theta d phi d theta, and then of course in the r hat direction. So that's ds actually. Now we actually have the whole thing. So we can say that this is equal to one of the integral, that is this guy just from 0 to pi for theta, and then phi goes all the way around. So we have from 0 to 2 pi for phi, and then we have from 0. Oh, this was annoying. Move this there. Yes. And then I have from 0 to, what did I say? Did I say pi over 2? Pi over 2, of course, 90 degrees. And then I have V0, so you can just put V0 outside. Then I have the field is just 0, 0, and 1. And we have to multiply that. Oh, that was the problem. That was the complicated thing. I have to z hat. I have to change that one, right? Oh, I could actually use not spherical. I could actually use cylindrical coordinates here. That would work, but I need z. This one I don't remember, so I just looked it up in some sheet. I have it here somewhere. So z hat in our case, let's see. I'm not going to draw it. It's unnecessary, complicated, and I don't need it. Let's see, z hat. Where is that z hat? There you go. So z hat or V0, V0 or V0 z hat. You can just write this in green. So V0 times z hat is actually the same as V0 times cosine theta r hat minus sine theta hat. This one I'm not supposed to remember, so it's all right. Okay, yeah. And of course, V0. Yeah. Did I do some mistake here? I have R. No, it's all right. But as we can see, we only have R hat. So of course, when I multiply V0, when I multiply that z hat component, of course that cosine theta is only one that survives. So I just get R squared. I can also move that one outside. That one isn't doing us any favor. Oh, stupid 0. Just missing that 0. So I can just move R squared outside. Then I have just sine theta, cosine theta, and then I have d phi. And then I have, which one was first? D phi is not the one that goes first, it's d theta, and then we have d phi. I should have actually done d phi first, shouldn't I? D theta is a little bit stupid now. Yeah. I don't have any phi, so let's do that. Yeah. Okay, so this guy right here is now just equal to V0 R squared. It was a little bit stupid, but who cares? So I just have 0 pi over 2, and then it's just, of course, 2 pi. 2 pi can also go outside. So 2 pi. Then I have sine theta, cosine theta. Then, of course, d theta. That's just u is equal to sine theta. And we get rid of that cosine theta. Then this just turns into V0 R squared 2 pi. And u is equal to sine theta, which means that when u is equal to 0, that integral is equal to 0, and otherwise it's equal to 1. So the answer is just V0 R squared and then 2 pi. Did I make some mistake here? I thought I got the same answer. Maybe I didn't get the same answer. I had then V0 pi times R squared. That's surface area. Here I just have 2 pi. Interesting. R, there's no integration in terms of R. No, maybe that's correct. I have 2 there. No, I have 2. There's something I did a mistake here. Oh, it's a mistake. 2 needs to go away. Pi R squared is of course correct. 2 is in the way. How did I get rid of 2 here? Oh, of course, it's going to be, I'm a moron, u squared over 2. That is what it is, and u just 1. So I get over 2. Yes, now it's correct. pi r squared v0. Yes. Very good. So that was the last task here. It's not, yeah. I actually just moved to that guy. It's displaying, yes, yes. Is thus the same dependent on, no, it wouldn't. It's just that we are fortunate with the vector field. I think it's like the reason why we get the same answer is that, let's say the vector field will go something like this for each vector. And then our normal will be something like this, right? And then I have a normal here, right? And then again, our vector field will go something like this again. Now, as you can see, it's only, I don't know, it's only the x that's contributing, but that will equal to the same as, what do you say, the same as just having that flat surface. I don't quite know. I just get the answer. I know the calculation, but why that physically, I'm not quite sure yet, but that's all right. Okay, this one is weird actually, because it's, well, I was like, where do I draw? Where do I draw that gradient? So this is actually not an xy plane, it's actually the height. And it's the height, and it's actually only affected by the x. So it actually, you could take it as z coordinate, it's only affected by the x. But we have to draw the gradient in the xy plane. So if I take that gradient, so what you can do is something like this. I'm going to switch soon. So if I have something like this, and since it's only in terms of x and not y, we have to just draw the arrows on the x. That's just it. So as you can see here, it's nearly 0 and it's negative. So it's going in this direction, right? And then it gets more and more negative. So you get bigger and bigger arrows, right? Then it gets flat, so that's 0, and then it gets very big here, right? Here it gets very big. I should have drew bigger arrows, but you get the point. And at the top there again, it's 0. Then the same thing again, just the opposite side. You get the idea. Okay. Where does the gradient has its biggest and smallest? Small, 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 and small, and small. Biggest is, of course, there, here, here, and there, of course. Yeah. Can the gradient be 0 in a point without the surface locally being a plane? Yeah, we know that from last semester. It's called a saddle point, right? Where you get that in the saddle direction and it goes like this, but you have a curve goes like this. You know what I mean. Saddle point. Just search it up. Okay. 7. Don't let the divergence loose. Your friend Q has given the task of describing water on a table. Water comes down from, I don't know what this word is, but from something where water comes from. You know, where you wash your hands, etc. In the origin, and it flows throughout the table. You can see that the water it has about the same thickness everywhere. Q has made this model where C is a constant. Yeah. Draw the field. Now the field is just equal vectors, just moving, right? And it just multiplied. So just get 10 if an x is 5. You just multiply everywhere by that constant. And you can see that as well, because V is equal to C over X and Y. That's just equal to, remember the divergence here of V. So I get this guy dot. The divergence is just partial. So C go outside. Then we of course just 1. So we just get C plus C. So the answer is just 2C, like that. Okay. Can you describe this field physically, right? try first understand what the divergence is telling. It's always just constantly increasing with the same value, and that doesn't make sense, because if water drops like this on the table here and it spreads in all directions, of course it should stop somewhere. That doesn't make any sense. So the model, I don't know if I'm going to program the model again. Let's just try. Why not? Okay. Just screw this here. So the model now, maybe I can just use this. Yeah, I can just use this. So it should just spread out. That's correct. But again, you should just get rid of it as well. So instead of Rx, you can just have normal Rx and normal Ry. I think that should work, actually. Yeah, that should work. You see, it's strong when the water hits air, and as the further we go, the more the water gets slower and slower, right? So that's correct. Okay, I think that's it for now. Yeah, perfect. And then see you tomorrow.